Okay, welcome back. This is now chapter 12. We sort of skip around a little bit in here. Spelling issues today. Exponential functions. Okay. See, it has that word exponent in there. So that's what we're going to be dealing with. And functions, we've dealt with square root functions, which is kind of the inverse to the exponential function. Not really, though. I mean, like this would have been y equals square root x. So that was a new one for us, right? We're used to doing stuff like y equals mx plus b. It should be some sort of straight line. Right? We want to introduce another one today. Oh, what else did we do? We did parabolas, these guys. Y equals x squared. So we want to introduce a new one today, which is the exponential function. And we'll take a look at graphing it. It's going to look like this, though. So y equals some base to the x power. So you're used to having a variable in the base. Now we're going to put a constant in the base and put the variable in the exponent. Right? So it's kind of like the reverse of this. So here I have the variable in the base and a constant in the exponent. Here I have a constant in the base and a variable in the exponent. Okay. And later on in this chapter, if we kept on studying it, and maybe in class we will, but not here online in the videos, this guy has an inverse function, which kind of undoes it, just like this guy and this guy are kind of inverses of each other. So the inverse to this guy is going to look like this. And you kind of see, this has parts of this in it. And what this is just kind of a weird flipping of this graph here. And this one is called log base b of x. Okay. So we'll spend our time mainly on this guy. We won't worry about this one in this class, but in the future classes, it'll be there. Okay, it'll be just like maybe in the previous class, you worked with this, but you did not work with this. Okay, so first we deal with the definition of this thing. And what is it? What does it look like? Well, like I was saying above, it has some number, some constant in the denominator, and then a variable in the exponent. The only constants we allow as bases will be values that are greater than 0 and do not equal 1. Okay. So b, again, we're calling that the base, and we've called it before the base. And the domain of this function, so the values that you're allowed to put in for x, so if you remember, there were values we couldn't put in for x up here. In particular, you can't take the square root of -2. So I can't put -2 in for x. And that's what we mean when we talk about domain. These are the values, the legal values you could put in for x. And it turns out for this type of function, it doesn't have any restrictions like this guy would. Right? It's just negative infinity to infinity. Anything goes. Right? Okay. How do I do this on my calculator? Usually you'll have one of two buttons. It would be y to the x button, or you'll have a caret button. And actually, when you're doing MyMathLab, you can use this button to get up into the exponent. If you hadn't figured that out already, you use this button on your keyboard. But usually calculators also have it. Okay, so let's get some 3 decimal approximations for the following. I have 3 to the 2.4. And so you put it into your calculator. I don't know how you would is type it. Sometimes you have to put the 2.4 and then you have to like do it backwards. Mine, you just put 3 and then caret 2.4 and it works. Okay, so let's see what I get. 3 clear. 3 to the 2.4. I get 13.96666. But if your number after the number that we're rounding to, and we're rounding here to the third digit, is greater than or equal to 5, you increase this digit by 1. So what it looked like is this, 666, and then repeating on and on. This number here is greater than or equal to 5. So if this was 5, 6, 7, 8, or 9, what you do is add 1 to the guy before it. Okay, so our approximation then is 13.967. Let's try another one. So I have 5 to the radical 3 power. So again, go to your calculator, 5, caret symbol, and then radical 3. Sometimes you have to put everything in the exponent in parentheses. This one is 16.24245, so 242 is the approximation. Okay, so one of the ones, maybe an example is in order here, where you have to use parentheses, is something like 5 to the 1/3. Okay, if I want to figure that out in my calculator, I'd have to kind of like do it like this. I'd have to type 5, and then type my caret key, and then type my 1, and then type divide, and then type 3, and then end. Oh, I forgot my parentheses. Dang it. Just freaking. Okay, so I type 5, and then I type the exponent key, and then I type my parentheses. That tells the calculator this is where my exponent starts. Okay, and then you go 1, and then you go divided by, and then you go 3, and then you end the parentheses. That tells the calculator where your exponent ends. Otherwise, it's gonna assume, if you don't include the parentheses, that really what you're doing is 5 to the first power and then divided by 3. Okay, so this right here is this. If you typed then 5 caret 1 divided by 3, you may think you're getting the right answer, but really what this is 5 to the first power and then this thing divided by 3. So this actually is 5/3, okay? Which is not what we want. We don't want 5/3. We want 5 to the 1/3. And 5 to the 1/3 is 1.7099, right? Repeating. And then following our rounding rule, we add 1 to the guy before it, okay? So that would be 1.7. And if I add 1, this will be 0, carry the 1, and I'll have 710, okay? Okay, so hopefully that will do it for us. Well, maybe one more. So number 8, we have this funny number e. Okay, it's not a variable. It's like the number pi. Have you seen the number pi? And everybody has Pi Day these days, and they all go crazy over it for some reason. This number is like the number pi. The pi number comes up when you're dealing with circles. This number comes up when you're dealing with compounding interest at banks and stuff like that. So it's a number like pi, and it actually equals something like pi. Let's see. I always forget what it is. It's 2.718, like pi is 3.14159. It's one of those kind of guys, okay? So it's non-repeating and non-terminating. It just goes on and forever. Okay? So your calculator probably has an E button on it somewhere. And so you hit that. And then raise it to the 3.4 power. If you got to put parentheses in, you do that. So this is 29.964. Yeah, 29.964. Okay. Okay. So let's graph these things. So I showed you a graph in the beginning. We have a bunch of new kind of, it's a new form for us. You know, eventually you're going to have a whole page full of these that you should be aware of. It depends, you know, if you're going to become like a scientist or something, they want you to kind of have an idea of what these look like. And right, so this is the one we're after right now, this picture. Okay, so how do we get there? Well, we can do a table and just graph the points. Okay, so graphing. And I'm just going to do a table. So problem 18, we have f of x equals 5 to the x. Right, and you could use your calculator to do this if you need to, but you don't have to. You can do them on your head. I'm going to go -2, -1, 0, 1, 2. Okay. And then you're plugging these x values into the exponent. So you'll have 5 to the -2, which is 1 over 5 squared, which is 1 over 25. Then I have 5 to the -1, which is 1 over 5. And I have 5 to the 0. Anything to the 0 power except 0 is 1. 5 to the 1 is just 5. And then 5 squared is 25. Okay, so may need a lot of tick marks, right? This is a big number guy. A lot of tick marks here. 1, 2, 3. Maybe I should go by twos, right? There's no way to win because this number is so small and this number is so big. You know, it's like, what do I do? So I'm just going to go by ones. One, it may be a little crazy, but here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, and then in these the x directions, I need to go at least 2. So 1, 2. Okay, so -2 is 1/25. -1 is 1/5. 0 is 1. 1 is 5. 1, 2, 3, 4, 5. And then 2 is 25. So if you've ever heard the phrase, it grew exponentially, this is exactly what they're talking about. Okay, it grows really fast. So it starts out kind of, you know, the speed at which it increases isn't very fast in the beginning. And this graph should be above the x-axis. It never touches the x-axis. I know it doesn't look like it. It kind of looks like it does in my graph, but it's because I had to smush it. Okay, so really it should always be above the x-axis. So it'll never touch this, but it'll get really, really super duper close as you go towards infinity in that direction. Okay. Okay, but this is the general shape of the exponential function. And there's one other form. So this is called exponential growth, but there's also exponential decay. And it's just basically taking this and rotating it around the y-axis. So you have to imagine a three-dimensional type figure. So let's look at the exponential decay version. Okay, so I'll look at number 22. And this will be, h of f of x equals 1/3 x. So I'll have x, y, and then I'm going to, again, use -2, -1, 0, 1, 2. The book may have you use -3 to 3. And it's really random. You can look at any point you want, but in general, you want to pick some points around the origin for doing it by hand. Right? But if you wanted to, you could pick like 100 out here and plot that. It doesn't matter. It's going to be way out there. Anyways, there's no mystery, hopefully, to how I'm finding these x values. It's just random. All right, so I'm going to plug these into the exponent. So I'll have 1/3 to the -2. Right? That's the same as 3 over 1 to the positive 2. Right? But then 3 over 1 is just 3. So I have 3 to the positive 2. And then 3 squared is 9. Now here I have 1 over 3 to the negative 1. So 1 over 3 to the negative 1 is the same as 3 over 1 to the positive 1. But that's just 3 to the 1, which is 3. And then anything to the 0 power is 1, except 0. And then 1/3 to the 1 is 1/3. And then 1/3 to the second power is 1/3 times 1/3, which is 1/9. Right? Okay, so let's go over here and plot these characters and see what kind of picture we develop. So this time I got to go up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going 2 in the x directions in either way. So at -2, now I have the tall number, right? So over here is at +2, I had 25. Over here it's -2, I get the big number. -1 is 3, 1, 2, 3 is right here. 0 is 1. 1 is 1/3, and then 2 is 1/9. And so you draw this smooth curve, shouldn't have any corners or bumps in it. It's the table I'm drawing on, it has some bumps. And then it goes in this direction, and it gets smaller and smaller and smaller, or in other words, closer to the x-axis as it goes in this direction. And but it'll never touch it. Okay? So if, you know, we call that phenomenon when it gets really, really close to something but doesn't touch it. It's an asymptote. Okay? Usually we're talking about vertical asymptotes that go up and down when you get closer and closer and don't touch. But this is a horizontal asymptote. We'll discuss that in this next section because we're going to talk about all the characteristics of these things. Okay? So anyways, this is exponential growth. Okay? And then this guy here is exponential decay. And you would see growth when you're talking about maybe a population of, you know, I don't know, bacteria, something like that. They grow very fast. You'll have exponential decay if you're talking about something like radioactive decay. So it takes a long time for radioactive elements to dissipate. That's one of the reasons why they didn't want to have those nuclear power plants, because that radioactive material is just around forever. It just doesn't go away. As x goes to infinity, the amount will never go away. It'll get close to 0, but it won't. You know, it'll never be 0. And I think that scares people. All right, so anyways, what are the characteristics of these things? Is there anything mentionable? And sure. First off, the domain is always the same. It's all real numbers. You can put anything into an exponential function, any version of it, and it'll work. The range then, if you noted from both of our examples, the output values, the y coordinate, so if I took any, looked at any y coordinate here, all of them are always greater than or equal to 0, right? And that was true for both examples we looked at. So all of these are greater than or equal to 0. All of these are greater than or equal to 0, the y values. And that's what we're talking about when we say range. What are the possible y values? Okay? And it's anything, any y value that's above the x-axis. So that'll be 0 to infinity. Okay. Nextly, there is a y-intercept. There's no x-intercept. Okay? It never goes through the x-axis, but there is a y-intercept. So for the y-intercept, you let x equal 0 in our function. So we have f of 0 equals b to the 0. And we said anything to the 0th power, you know, besides 0, but b can't be 0. Anything to the 0th power is 1. Okay? So the y-intercept then is, well, we said x, we let that be 0, and then the output, the y variable, or the y value is 1. Okay, what else? Well, we have this asymptote thing I was talking about. It's a horizontal type, horizontal asymptote. And it's basically this imaginary force field that the line gravitates towards. Okay? So in our case, it doesn't actually even go through that imaginary force field. It just gets really, really close. In some cases, when you're dealing with horizontal asymptotes, it can go through it. Okay? If you studied asymptotes before, you know the vertical ones, no, it's not allowed to go through a vertical asymptote. But horizontal ones, you can go through it, but in this case, it doesn't. Okay. So anyways, what is the equation for that? It's the x-axis, and the equation for the x-axis is y equals 0. Okay, so the pictures then, the first picture we saw was the exponential growth picture. It looks like this. And that's when the base is actually greater than 1. So let me write that. This is a picture of f of x equals b to the x, where b is greater than 1. Okay, then the exponential decay version, so it starts out big and then it gets smaller and smaller and smaller with respect to y, the height. This is a picture of f of x equals b to the x, where b is some sort of fraction value in between 0 and 1. Okay. And that's what we saw in our examples, right? So this base value is 5. It's greater than 1, so we had the exponential growth. This base value was 1/3. It's between 0 and 1, so we had exponential decay. Okay. One thing you'll study after a while, once you get to college algebra, is the results of adding things in and subtracting things away from this kind of parent function. Okay? So what you'll have is a bunch of parent functions, and then you'll be able to figure out, like, for example, if I was given y equals x squared, and I wanted to draw y equals x squared plus 1, okay? I could do that just by moving this thing up one place. Okay? So it's a quick way to graph these things if you know what the parent looks like, the parent graphs. So this next problem, that's kind of what you're doing. You're comparing and contrasting two graphs. And one is just a translation of the other. So problem 30, they want you to graph f of x equals 2 to the x and g of x equals 2 to the x plus 2. Okay, so if nothing else, you can always do tables. Okay. So I'll try -2, -1, 0, 1, 2. And first I'm getting my table for 2 to the x. So I'll plug -2 in for x, and I'll have 2 to the -2, which is the same as 1 over 2 to the 2, which is the same as 1 over 4. Okay. Then I have 2 to the -1, which is the same as 1 over 2 to the 1, which is just 1 over 2. Then I have 2 to the 0, which is just 1. Then I have 2 to the 1, which is 2. And I have 2 to the 2, which is 4. Okay, now I'm going to do a table for g of x. And we're going to notice some relationship between the two tables. Okay? And I'm not going to, in the y part, I'm not going to sort of combine things together. I'm going to leave it so you can see hopefully see the pattern. So -2 will give me 2 to the -2 plus 2, which equals 1 over 2 squared plus 2, which is 1 over 4 plus 2. So I guess you can already see that what the pattern is going to be. This graph is just the same as this graph, except every y coordinate is going to be shifted or increased by 2. So -1 is 2 to the -1, which is 1/2, but then you have to add in 2 on the y coordinate. Okay? So I think that's enough, and we'll be able to kind of get the picture just by moving all of these coordinates up by 1, or sorry, by 2. Right? So let's try it. Okay, so if I need about 4 tick marks, 1, 2, 3, 4, and then 2 in either direction on the x-axis. I'll draw this guy first. So I got -2 1/4, -1 1/2, 0 1, 1 2, and then 2 4. I'll connect my dots, and there's f of x. And then what I was saying is all you have to do, if you know this, what is this coordinate here? This coordinate is -2 1/4. In order to get the new coordinate on g of x, all I need to do is move or add 2 to 1/4, which comes down to just moving this coordinate up 1, 2 places. Okay, so it's seriously, that's all it is. It's just move this guy up by 2. So it'll be 1 1/4 and then 2 1/4. Okay, and then same for this. You're moving the y coordinate from -1, 1/2 to -1, 2 plus 1/2. Okay, so you move from 1/2 to 1 1/2 to 2 1/2. And then you're moving this guy up 2, so that he'll be there. You're moving this guy up 2, he'll be there. You need some more tick marks. And you're moving this guy up 2, and he'll be there. So the new graph is basically just the old graph, but shifted up 2 places. So let's try to draw it. Right. One last thing is the asymptote. You don't usually see the asymptote. It's right here. Okay, that's that line that this gravitates towards. Okay, y equals 0. When you shift this guy up, the asymptote will actually move with the graph. It comes along for the ride. It's its friend. I don't know what they call those little fish that attach themselves to the sharks. It's like one of those. Okay, so the new equation for the new asymptote is y equals 2. Okay, so after a while, you know, you'll sort of automate this process, and you'll say, okay, if I'm given this, I know in my mind what this looks like. So to draw this, all I have to do is move this one up 2 in my mind's eye, okay? And you'll be able to graph an infinite number of graphs just based off of these translation ideas. Okay. Next, the last thing we'll talk about is the natural base e. Right? So this was that number that I talked about there for a second. It's like pi. Right? So section 5, the natural base e. Right? So e, like pi is 3.14 whatever, e is actually 2.718281828446, blah, blah, blah. Okay. Goes on and on forever. It is non-repeating and non-terminating. Okay. So people kind of, I bet you there's some people kind of think of it as kind of a random number generator. So if you're going to do a lotto, you could like go far enough out and E and kind of just pick numbers that way. And I think that's why it works. Randomness is a really interesting thing. It seems like it's all over the place in our society. So you know, it's not something you go and study, and it doesn't really have anything to do with anything you do. No, every time I go out with my friends, they want to play the lotto and stuff. This randomness just seems like a fascinating topic to get into. Right? I don't know though. It's up to you. Anyways, part A, where do we see this number E? And what I said is it comes up in financial matters, okay? So financial matters have been around forever. And I was reading an article that said like they found a tablet from 3000 BC that had financial records on it. It's crazy. So it's almost like this number has probably been around a lot longer than, well, I mean, pi itself. Pi is more famous, but E is probably more usable. It's more pertinent to our our financial matters in life. And where does it come up? It comes up in compounding interest. Okay? So there's all kinds of different ways to compound interest. If you are in a money and you like go to the bank and maybe you are renting to people at this point, I don't know, or you are paying rent to somebody else. There's all kinds of different compounding periods possible. So you can compound once a year, and in that case, you can figure out the amount you have in your account after 1 year by using this formula: A equals P times 1 plus R to the T. Right? So A is a future amount. R, well, I guess we should go P next. P is the amount of money that you have in your account. It's like it's either the money that you deposit or the money that you've been loaned. Okay, so this is like a down payment, or it's a principal. Basically, that's why it's called P. It's principal. The R is the rate, the rate of interest in your account. So when we're using the equation, we'll use it as a decimal. And then T is for time. In this case, it's a number of years. Okay, so we could use this formula to figure out yearly interest. Then you can also compound n times years. So you can have monthly compounding, daily compounding. So in that case, the formula will be A equals P times 1 plus R all over n to the n-th power. Okay, so n is the number of times you compound per year. And then you may be asking, well, what does this have to do with that funny number E? Where does that come about? Well, it comes up when you keep on making your compounding period smaller and smaller. So if you go, monthly compounding, then weekly compounding, then daily compounding, then hourly compounding, then minutely compounding, then second compounding, et cetera, et cetera, et cetera. Eventually, you have continuous compounding. Okay. And there's some math involved, which isn't all that advanced, but we just save that for your next class. But if you do the math, you'll end up with this equation: A equals P E to the RT. Okay, so it's kind of like you're replacing this stuff with the number E. Okay, so at this point, we're just going to look at an application, and it'll turn into a plug and chug. So they just want you to plug some numbers into those formulas. You'll need your calculator. So this is 40. Find your future value, or find what the book calls the accumulated value. Your principal, or maybe the money that you currently are putting into your account in the beginning, is 5,000. So you put 5,000 in your account, and then we want to know how much you have after 10 years with an interest rate of 0.065, which is 6.5% interest. Okay? Okay, so first they want you to figure out semi-annual interest. Okay, so for semi-annual, the end value is 2. You're compounding twice a year. Okay, so you go back to your formula, and we'll have the accumulated value, or the future value, is 5,000 times 1 plus R all over n to the n times t. Okay, so it's a big, ugly expression. I'll give you a little bit of practice with your calculator. And at the end of 10 years, you should have $9,479 and about 19 cents. And that's approximation. Let's go to monthly interest. And and see what happens. Do you think you're going to have more money if you compound more? You know, or is it not going to be as good? What happens there? Okay, so again, you're plugging it into that formula, 5,000 times 1 plus 0.065 all over, whoops, monthly is 12 times a year, right? All over 12, and then raised to the 12 times 10 power, so 120. So I have, putting it into my calculator, $9,560.92 approximately. Right? So compounding more gives you more money after 10 years. It's not much, but it's more. So you want to compound more, and then ideally you compound continuously, because I think that would give you the most money, right? So let's see, continuous compounding. And we use our formula, PE to the RT. So our principal is 5,000. And then E to the rate, 0.065 times 10 for 10 years. Okay, so let's see what we get there. And I'm getting $9,577.70. Okay. Okay, so we'll leave it at that for now, and we'll continue on with this. There's just one other section we want to look at concerning exponential growth and decay, and then we'll be done. Okay, thanks for watching.